Okay, well, thank you everyone for attending today's workshop. My name is Taylor Kern, and I'm the Senior Coordinator of Member Engagement here at the Toronto Board of Trade. Thank you for joining us this afternoon at our value-membered Mphasis workshop on transforming business using quantum computing. In this workshop with Mphasis, you will gain a deep understanding of quantum computing and explore its transformative potential in tackling business challenges with quantum AI, optimization, and simulation solutions. Before we begin, I'd like to acknowledge this land that we are meeting on, which is home to diverse First Nations, Inuit, and Métis people. Though you could be joining us or watching from anywhere, the board's offices are located on the traditional territory of many Indigenous nations. They share with us a sense of responsibility, intergenerational equity, the well-being of today and tomorrow. And now, without further ado, I would love to pass it over to Vivek and Rohit, who are going to be today's hosts on your workshop.
Thanks, Taylor. Hello, everyone. I'm Rohit. So what I'll do is I'll share my screen. Just give me a minute. I hope everyone is able to see my screen. Taylor, could you please confirm that?
Yeah, you just got to put it in presentation mode there. There you go. Perfect.
Yeah. So hello, everyone, once again. So as Taylor mentioned, I'm going to present quantum computing and its applications for industries today. So just a brief about me. I have around 14 years of experience with 8+ years in data science. Currently, I'm leading the quantum computing initiative at Mphasis Next Labs. And I hold a bachelor's degree in electronics and communication and a master's in business administration. I have developed a lot of AI and quantum computing based solutions and delivered client projects in areas of BFSI, logistics, among others. So the topic for today now. So this is the agenda. That is what I'm going to do. First, I'll just a brief introduction to the team I am part of, Mphasis Next Labs. Then we'll jump into quantum computing, what and why. Where do you apply quantum computing? Then what is the state of quantum computing today? And finally, what we at Mphasis are doing in area of quantum computing. So first of all, the introduction to Mphasis Next Labs. So Next Labs is Mphasis R&D arm for research into disruptive technologies and taking it to the market. So we focus in areas of cognitive, cloud, and quantum computing. On the left-hand side, you'll see a lot of solutions that we have built in the traditional AI, that is like solutions like MLOps, solutions like customer 360-degree analysis, process mining, and others. These solutions are available, and we have used these to solve our customer problems. Then next, more recently, we are focusing on generative AI. In fact, we have launched a unit called Mphasis.ai, which is our business unit to address AI-related problems. Here we are working on large language-driven models. We are looking at synthetic data generation. We are looking at ML governance issues, which are coming up across the world, given the use of decision-making through AI. Under quantum computing, we are looking at algorithmic development and deployment, assessment and consulting service, ML optimization and process simulation-driven solutions. So I'm going to talk about this today. Since we are an R&D-driven lab, we do a lot of thought leadership. We have around 5 awarded patents. We have 20+ AI and quantum computing white papers published. And since we also address customer use cases, we have a design thinking-driven consulting model, which allows our customers to identify, rank, prioritize, and execute quantum AI and quantum use cases. We have a lot of partnerships with academia and industry. For example, we are partners with AWS, Azure. We are premier partners with them for the AI side of things. We have a partnership with University of Calgary here, where we are the anchor business partner for the Quantum City initiative they have taken. Other than that, we are also partners with Alberta Machine Intelligence Institute in area of solutioning for business problems. Now, generally, our output consists of customer projects, industry-oriented solutions, and marketplace listings. We have around 250+ AI and quantum computing marketplace listings. So if you go to AWS, generally you will see we are in the top 3 always. So you can use these solutions to solve your business problems. Or if you want to scale your business problems, you can reach out to us by looking at what is the art of the possible. This is a brief introduction on Next Labs. Now the topic for today, quantum computing, what and why. So I will take a drill down kind of an approach here, where I'll just explain what quantum technology in general is, and then I'll go into the computing side of things, so bear with me. So the idea is that the first quantum revolution has already taken place once we were armed with the knowledge of behavior of subatomic particles and structure of the atom. A lot of new technologies were which basically got translated into integrated circuits, which created your computers. You know atomic clocks for GPS. You know about lasers, very, very important, MRI machines, electron microscope. All these were made possible because the physicists identified the behavior of subatomic particles. Now, more recently, we have moved into the second quantum revolution. It started around, say, early 80s, where somebody thought of using quantum mechanics to build technology, a different type of technology. So if you look at it, it is very, if I have to make a comparison, it is very similar to our current digital electronic technology, where the idea is to build sensing machines, computation machines, communication networks, and encryption systems. You know about the internet today, you know about our RSA protocols and all. These systems generally fulfill the human need to communicate, to compute, to encrypt messages, and to measure things. Same idea is taken from a classical domain to a quantum domain, where we are again trying to build similar things, basically sensors, computers, communication networks, and encryption systems. But the underlying technology that we are going to use is quantum physics, quantum mechanics, rather than the classical physics of today. Quantum computing is a part of this revolution, the other being the sensing, the encryption, and communication. The difference generally lies again in the way the computation is done. It uses certain concepts like superposition, entanglement, interference, and tunneling to solve certain problems with a significant performance advantage. We have to keep in mind that a quantum computer cannot solve all problems that you have today with the same efficiency or very much efficient than the current computers that we have. So it is built for specific problems. Now, we talked about quantum technology a little. I want to talk about computing now. So if you see on your screen right now, I have put different type of computers that have been conceptualized or created over a period of time. So if you have to understand computing, the most familiar object that you can look at is the human brain. The idea is that human brain looks at the real world, takes that information, and be it images, be it sound, be it tabular data or whatever, it creates a picture, it creates an abstraction for the same, which our brain can understand and process the same. Now, keeping this idea of data representation and data processing in mind, different machines can be built to do the same task. So you can think about searching an item in a database, or sorting a list, or building an AI machine. All these tasks can be done using different computers. We have to keep in mind that computing is a physical process. You may write a software program to execute your computation, but at the end of the day, there should be a physical substrate, underlying physical substrate, which does the computing. So in alternative forms of computing, in DNA computing, for example, you make use of DNA strands to encode information and process them. You can build a search machine using a DNA computer. Similarly, with chemical computers or Babbage's mechanical computers, some similar things can be achieved. But more recently, we have been looking at electronic computing rather than the other forms. And here we have taken a path since 1950s, let's say, where we have moved from vacuum tubes to transistors to integrated circuits, which have now we have converted into your CPUs, your graphic processing unit, your DSPs, and others. And then we have built supercomputers using the same thing. The most recent advent of this is a quantum computer. It uses a different form of data representation and a different form of processing elements, which gives us certain performance advantages for some type of problems. Now, the advantage is exponential in nature. Things that may take, say, a million years on a classical computers for certain tasks can be done in milliseconds on a quantum computer. So we have to keep that in mind. For certain problems, this advantage is available, and hence this area is being currently pursued. Now, look, coming from quantum computing to quantum computing, these are some key ideas that you have to look at. The idea of representation of information. The information that is available to you in the real world will always comes in form of images, text, sound, tables, whatever it is. But the different computers represent it in different way. In case of our digital computers that we use today, it is a 0 and 1 representation. That is a binary representation. Your images, each of those pixels get converted to a number. That number can be converted to a binary formulation, which is then processed. In case of quantum, that representation does not take only 0 and 1 levels, but a combination of the two. This increases the way the information density, as well as the algorithms that process that information, their capability for certain type of problems. So this qubit representation of information is very important. It is, I generally look at these kind of representation in form of a language. Your quantum computer understands a different language from a human computer like me versus a digital computer versus a DNA computer. So that information may remain the same, but the representation of information is different, which gives it particular advantages. From execution stand of the processing point of view, you can look at superposition, entanglement, and interference as things which allow you to do faster processing in certain cases. Now, these are complicated topics in themselves, so I won't jump into it, but you might have seen interference in lakes, right? So that concept, if brought down to the atomic level, allows you to build computers. That's the main idea. Now, the second idea is there are multiple types of quantum computers that exist. Some are universal in nature, that is, you can solve almost any problem on it. And for example, you want to build a sorting machine, a searching machine, AI machine, any sort of machine can be built on those. These computers are gate-based, very similar to what we have today, that we use today, your laptops, your supercomputers, your mobile phones, everything. But there are other ones as well, which makes use of quantum physics at the back end, but solve a lesser number of problems. So quantum annihilers is one type, which mostly is focused on sampling and optimization kind of problems that occur in everyday life. Now, there are different camps of quantum computing. When I say camps, the idea is that quantum computing is still a new field. It is progressing rapidly. Hence, we can divide it into two parts. One is the useful quantum computers of today. They are available today. You can make use of them, and you can solve certain problems. These are called noisy intermediate scale quantum. That is, they are noisy in nature, and they are smaller in size. And second is the quantum inspired part of it. These are not quantum computers, but classical computers, which are inspired by research into quantum computing. So these gives you some advantage. It is not 1 million years into 1 milliseconds, but say 10 years into 4 years or that sort of a thing. Now, in the future, once we solve the problem of noise as well as the scale that we are looking at, we can get exponential power, the 1 million years into 1 millisecond. These are called fault tolerant large scale. And this path is progressing very rapidly. People are able to, they have made significant progress in error correction as well as scalability of things. So it is not too far away in the future. Now, what if they become available? What will change? The impact we have to know from business standpoint, from societal standpoint, from other standpoints, right? It's a disruptive technology. It will change the world completely. Think about when the classical computers came into existence or when internet came into existence. Sorry. This is the level of disruption we are looking at. In fact, more than that. The gains will be exponential in nature. If you can think about things running in 1 millisecond, you can do drug discovery on click of a button. which takes years today. You can discover new materials which have properties which can take you into, say, through which you can build batteries or systems which can take you far away into space, which is not possible. So those kind of discovery gains are possible. And then it will impact core systems. We are not looking to solve peripheral problems, but very core problems like portfolio optimization, like last mile route optimization, network design, drug discovery. So very significant technology when you look at the type of use cases we can address using this technology. I'll go to the next slide. So where to apply it? So before we talk about where to apply quantum computing, what are the current focus areas? So not each computer is built to solve each problem. So if you look at your GPUs today, right, they are used specifically for graphic processing or running AI workloads. If you look at neuromorphic computing, they are building processors which address a specific task. Your gamers have physics chips available or audio chips available to process sound or do a computation on physics of objects. Similarly, so all these becomes co-processor. Quantum computer will also be a co-processor. And right now, the areas that we see where most focus is given is in area of machine learning, optimization, and simulation. So simulation, when I say it has different connotations in different scenarios, but I'll say it is a natural process simulation, where you can look at systems where atoms interact to produce results. So drug discovery, chemical reactions, all these come into this area. Now, what is the industry doing in this area, right? So we talked about the focus of algorithms and machines and everything, but is industry adopting these, doing something with these computers today? So yes is the answer. So I have sorry, divided this slide into three areas: finance, logistics, and others. In the area of finance, if you look at the slide here, a field called quantum banking has itself come into existence, and you can read about it. But the use cases that are considered in the same is enhanced credit screening was taken by Trade Tech. Portfolio optimization was taken by Nomura, Barclays, and BBVA. Goldman Sachs looked into security pricing, and so on and so forth. One of those case studies from BBVA, where they used a machine from D-Wave, which is a quantum annealer. They used the hybrid solver of it. That is a classical quantum machine. The number of portfolios that was possible on the data was in tune of 10 to the power 382. Now, this is a huge number. You have to find a few portfolios which give you the best risk return profile. Not easy for a classical computer to do the same. So around 171 seconds of runtime was taken by building this solution, which is a very small time when you look at the possibilities. They found portfolios of around 60% return with 15% risk, and they achieved a sharp ratio of around 12 for certain portfolios. These numbers are huge. When they used the some classical solution on the same data, their range of returns was -20 to +20% for a risk of 15%. So you can see that better risk return portfolios can be identified using programs built on this technology. Sorry. So now I'll go into the logistics side of things, and I'll take two case studies. One is from Toyota Systems. They wanted to solve the automotive part supply chain optimization problem. More than 3 million routes were there to their dozens of factories, and they wanted to find the most efficient routes. They used the quantum-inspired technology here. It's called digital annealer, similar to a quantum annealer, and this is provided by Fujitsu. There was around 30 minutes of runtime, and they said that it could cause a potential reduction in cost of 2 to 5%, which is a big number given the size of the operations. Other one comes from Los Angeles, Port of Los Angeles, basically, where they wanted to optimize operations in their third largest terminal, Pier 300. They handle more than 1 million containers per year and 5,000 trucks a day. By building a quantum computing driven solution, they were able to increase deliveries by 62% per day per crane to their dozens of factories and double their throughput and almost half their RTG movement. Another interesting one is performance modeling of jet engine designs that was taken up by Rolls-Royce. They want to achieve net zero carbon emissions by 2050. They looked at a hybrid methodology, GPU and QPU, and this is happening both given the size of quantum computers today. They are being used in a hybrid mode with other processors like GPUs, which allows them to build scalable solutions. Now, this is a very complex solution that they built using NVIDIA's GPU-based framework. There was around 10 million layers and 39 qubit quantum circuit. It's basically a gate-based system that they made use of to solve this problem. So they are also looking into it. And you can look at a lot of use cases here: drug development, real-time risk modeling, waste management, all those things. Now, where is quantum computing today? So before we jump, so somebody is trying it out, it does not mean that this will be the future. But if we look at some indicators, it's possibly will make sure that you have it available for your own execution, as well as people are putting money into it. So the first angle I will look at is the strategy and investments going into quantum computing. So it has been estimated by McKinsey that it will be around $106 billion by 2040. This is whole quantum economy, not just quantum computing. This includes sensors, telecommunication networks, encryption systems, everything. Governments, more than 10 countries have invested over 1 billion USD in this area. 250 quantum computing startups and have been launched, and 36 of those were launched in 2022 itself. From 2020, the rise of number of the investments, the number of companies, all has been exponential due to the advancement in research. Sorry, there was a startup investment of around $5 billion USD, and from 2020 to 22, and 7 deals in 2022 were greater than $100 million. So VCs, governments, everybody is taking notice and investing here. Universities are also taking notice, where 50 quantum technology master's degree program and 180 universities have launched quantum technology research groups. And there has been establishment of R&D driven quantum ecosystems such as Quantum City. So these things indicate that things are moving fast and in the right direction. Now, what is coming out of it, if you look at it, we are rebuilding the whole tech stack. We are looking at the hardware, the middleware, the system software, the application software. So through this research, a lot of money is going into hardware today. All these companies that are listed here, some already known, some new, have built quantum computers. With atom computing, just a few days back, they launched a 1,180 qubit computer recently. To give to put some value to that number, 50 qubit machine, if you look at, it will surpass a supercomputer today. 50 qubit properly built machine where all the qubits are connected to each other, it can surpass a supercomputer. But since they are noisy, since they are not well connected, 1,180 is still a leap, but still behind what we can do today. Now, hardware is being done. System and application software is being developed by Fujitsu, CQC, NVIDIA, and others. And all this is made available over quantum compute as a service providers. So yeah, Azure has its own service, IBM has its own service, AWS has Xanadu, and so on. So you can see that an ecosystem is coming up, money is flowing in. You can make use of these systems to build your solutions today. Now, what we are doing with quantum computing at Mphasis is an interesting question. So we started this area around 3.5, 4 years back. And our goal, since it was started in Next Labs, the goal was to take this disruptive technology to the market. And when we did that, we looked at these these 7 areas specifically. And I'll talk about a few. So our focus has already been applied R&D driven. So we look at the fundamental research that is being done in this area and how we can convert that to softwares or applications which we can take to the market. We have built, in that vein, we have built industry-focused solutions. We have done partnerships with academia and industry. We have written a lot of white papers. We have done a lot of webinars. And we have also created a design thinking driven engagement model, which allows the customer to adopt quantum computing. Our industry solutions will fall in these areas: optimization, AI, simulation, and finally, we're partnering on cybersecurity, cryptography, and other things. Now, this is our solution portfolio. So it is mostly quantum machine learning and optimization portfolio. And if you look at it, the solutions that we have built are in area of logistics, supply chain, life sciences, the airlines, all these areas. So last mile route optimization is one where we look at the delivery of packages to the end customers from a depot, from FedEx, UPS, and others. Portfolio optimization, we have applied it to building risk return profile for stocks from Dow 30, S&P 100, NASDAQ 100. Brain tumor detection, we have applied quantum machine learning for image processing. Similarly, we are looking at feature selection for high dimensional ML. It is a complicated process today if you want to run high dimensional machine learning models. Sorry, because it consumes a lot of compute power, and that basically increases the runtime and compute requirements for the same, and you may not get the right quality of result. Quantum provides a method to identify the right features to build a more accurate and more generalizable model. So a lot of things we have done. Airline crew scheduling is another one where we look at how we can allocate crews to how we can group different flights together and then assign crews to them at minimal cost while maintaining all the constraints that coming in. It is a very complicated problem, and we have built a solution around it as well. So what I'll do for now is I have more slides, but before I keep talking, I'll show you two demos at least that we have built internally, and so that you can get what we are trying to build using this technology. It is very similar to what we built today, but just using quantum computers at the backend. So I'll stop sharing and I'll reshare my screen. Somehow, yeah. I hope you can see my screen. So this is a portfolio optimization and asset allocation solution that we have built. The idea is that if we can apply quantum computing to portfolio optimization problem. So this is a recorded video because running the solution still will take a little longer, if not years, like in the classical computers. If I play this, so if you see, we have looked at three different stocks, Dow 30 stocks, your NASDAQ 100 and S&P 100, and I'll show you all three one by one, and I'll compare it against a classical solution. So we have selected the Dow 30. We have taken data from Jan 15 to December 19. We did not take recent data because when COVID occurred, everything changed. So we looked at that 5 years of historical data to create the forward-looking risk and return for each of the stocks in Dow 30. Now, taking that as the base, the statistical return and statistical risk for each of these stocks, we tried to combine these different stocks together to build portfolios which will give you the best risk return. So I'm showing the first one. This is just a descriptive page. You can review the data and then you can run the portfolio optimization. So once we press this button, the quantum engine is at work. This is running on D-Wave. So this is the first result. Now I'll explain this a bit. So if you see this portfolio frontier, which is the most important graph here, the blue dots are a classical solution, a classical Monte Carlo enhanced solution that we have built, where it generates different portfolio. Each dot is a portfolio. And the amber ones here are the portfolio generated using a quantum computer. Now, if you look at these two, you will see some advantage. For similar returns, you can find some portfolios with a lower risk. Now, given it's a 30 stock thing with 1 million invested, classical computer can handle it in a good way. Let's see what happens when we go to the next solution, the next indices. So right now it shows some annual amount. This is the yearly return. And also we choose NASDAQ 100 and let's see what happens here. So I'll directly jump into the results. Now this is interesting. If you see again, the amber dots are quantum, the blue dots are classical. For the same portfolio risk, you find a lot of portfolios with a better return. So classical could not do it, quantum did. Now this is the second one. Each of these graphs here basically show how much should you invest in each of these stocks. We have limited it to 10% at most for each stock because there will be market limits to it. This is not exact replication of how market works, but for a comparative solution with a classical system, this works well enough. Now, if we go to the last one, this is S&P 100, and here the results again are phenomenal. So if you look at it, the classical solution basically for the same risk range, the returns are very high and vice versa. So this at least establishes to a certain extent that quantum driven solutions have some capability to surpass what is available classically today. So this is the first demo I wanted to show. Unfortunately, I'll have to stop sharing again because Zoom is not allowing me to share the other demo in the same application. So I'll share again. Just hold on, please. Yeah. Now, I hope you can see my screen again. Now, this is a last mile route optimization demo. As I said, if you look at companies like FedEx, UPS, and others, their goal is to send packages from point A to point B. The structure it takes is that there is a city station where the packages are collected for delivery or pickup, and then they are sent over in a hub and spoke model. So the last part of it, which is connected to the customer for pickup or delivery, is where a lot of cost goes, around 53% cost according to one of the reports. If you are able to optimize the distance traveled by different trucks given your fleet, you'll be able to save a lot of cost. And in that vein, it's a very complicated solution. Think about if there are 10 drivers, 5 time windows, 100 packages, or 10 packages, it is 10 into 10 into 5, 500. The number of solutions that become feasible are 2 to the power 500, a very large number. And FedEx and companies like these operate 20,000 packages with thousands of trucks at some of the locations. They're not able to solve it using any optimization software available today, but rather they break down the problem into smaller pieces, which is suboptimal in nature. Quantum does have the capability to handle the larger problem in one go and give you the most efficient routes. So this is the landing page where we start. Now here what we do basically is we select a new data set. Here you provide the capacity of the vehicle. You can give your own fleet also, but we are giving only the vehicle capacity. Now you schedule your pickup and delivery for the day. So for today, let's say. So now you have the depot and the customers, what is to be delivered, how much to be delivered. This is the depot, this is the location, how much to be delivered, where to be delivered, what is the time window in which it is to be delivered. So now what we do is we basically review that data, and same thing is shown on the graph. Now you run the quantum optimization engine. It runs, and finally, if you see, it assigns to each customer a vehicle. So this is after after identifying the number of vehicles required, and secondly designing a route after that. How much, which package should go to which vehicle, basically. And on the right hand side in the chart, you'll see the different colors indicating different trucks, and P and D saying pickup or delivery, with customer IDs and vehicle combined together. Now you can review these, you can move on and go to the next level. Here, basically, we showcase some KPIs with respect to our solution. So if we see total time taken is 19 hours, 616 miles covered, $185 of fuel cost given some mileage and cost of fuel, cost of per unit fuel as considerations. Also, did we miss any customers? Was there any overload in any of these vehicles? All these are important things that we have to consider when building a solution. Now, if we go here, we can go vehicle by vehicle and see the routes that have been designed using this new algorithm that we have put into place. It gives you the order, it gives you the time, it gives you the customer, everything. It goes down to vehicle level details, distance traveled per vehicle and all. Some different KPIs. Now, since this is a pickup as well as delivery, it also shows vehicle load by time. So when the delivery happened or pickup happened, whether anything was overloaded or offloaded, all that is shown in this graph. So we are building the next version of it, where we are not just considering the weight constraints of the vehicle, but the volume constraints. We are looking at equitable distribution of work in this case. All that is being developed. This is a second demo. And given we have some time, I would like to show one more demo here. I may have to again share my screen. So let me just open the demo and then I'll proceed forward. Yeah, I hope you can see it. So this is airline crew scheduling, very important. This problem, basically, if you look at what happened during Christmas when the different flights were landed and nobody knew how to reschedule and all, these problems become very important. They're large scale problems, not easily solvable, and some sort of computation compromise is being done today to get the solution. Quantum computers gives you a way to solve these problems in their entirety. And in this way, we have built this problem. This problem is called airline crew scheduling. It is a two-part problem. First, you are given a monthly schedule of some airlines, say United, Delta, or WestJet. From that monthly schedule, say of 500 flights, you have to create certain groups based on constraints. Now, these constraints are no two flights should overlap. There should be a gap of 1 hour between each flight. These sort of constraints are put by labor organization, airlines, operating team, airport operating team, all those. Now, considering those constraints, you have to create these groups. Say you create 10 groups of 50 flights each, easiest solution for now. Now, to each of these groups, you have a crew which are at certain base locations. These crews are to be assigned. Now, again, there are constraints when the crew is available, how many hours they should work, all those is considered. So the first part where you have to form the groups is called airline crew pairing. The second part where you have to assign crews to the group is called airline crew rostering. Now, again, we'll start with a new one. Here you have to give the monthly schedule first. So upload your new flight schedule. Now, all this is done. You add certain constraints that I talked about. You can see flying hours of the group, the number of flights in the group, the inter-flight rest time, duty period, all this is to be considered. So once you do that, we are showing some dashboard one. So this is a real world data of one of North American airlines, which had 1,013 flights around 26 different airports with 34 median flights per day. This dashboard that you see right now, we are trying to establish the complexity of the problem. So if you see flight departure by day, by hour of the day, by flight frequency per day, those sort of things we have shown. You see a lot of overlap between flights from the same airport or same arrival and departure airport combination. So it's not easy to solve this problem through any method. Now here we are solving the first problem where we are finding groups called pairs from this initial data. Now, if you see, we have found some pairs. For each pair contains certain number of flights. And if you see, each flight leg has been assigned a pair. Now, if you look at each of those pairs, some number of flights are assigned. Now we have compared this between quantum and classical, and quantum is working well. And we have to keep in mind, these are new, smaller computers, and still they are almost either breaking or matching the performance given by classical computers, and they're progressing rapidly. So some comparison by each pair, what are the flying hours, what are the overall hours, all these become important. This is the first problem that we have solved. In the second problem, we have to supply the crew data. So at 3 different bases, the crew are available. We upload this data. Now, again, you have to supply certain constraints from the crew. So rest period for the crew, the flying hours of the crew, the overall hours, the number of crew members per flight, all that is to be given. And again, the second problem is solved for each crew. We have given the flights that they're going to cover, in which pairing they'll be allocated. All that is given here. Sorry. So again, we have done a classical quantum comparison here to showcase what are the results. And though this is a demo, I would encourage you to look at the white papers. They are available for free on our website, where we have done a detailed comparison of the different solutions we have run. And as what we have found that as we increase the size of the problem, classical computer stopped giving solutions altogether. We waited for, in fact, 3 days, no solution. Quantum computer was done, say, in half a day. Basically, in fact, every optimization problem has two parts. One is a formulation part where you encode your objective and constraints programmatically. Second is the solver part. In the classical world, both are time consuming. Solver is more time consuming. In quantum case, solver is not that time consuming. Sometimes it takes just 0.7 seconds or something to return the results. So this is where I stop with the demos. And what I'll do next is I just go back to the deck. Yeah. Sorry, my mouse is behaving erratically. Yeah, so this is where we were. Now, we talked about what we have built, but nobody can do quantum alone in this world. It's a very complicated field. You need academy on your side. You need tools and cloud providers on your side. So our ecosystem is built in two places, India and Alberta. Alberta is our quantum headquarters. In India, we are one of the two industry partners with Government of India for their Quantum Computing Applications Lab initiative. We have partnered with IIT Madras, where we have opened our own quantum computing research lab. We are partners with Krishi, which is a startup working in this area, again founded by a team from IIT Delhi and other universities. In Alberta, we are anchor business partners with University of Calgary. It is called Quantum, their initiative called Quantum City. We are partners with Calgary Economic Development, Alberta Government, and Invest Alberta. And we have a shared ecosystem of providers such as AWS, D-Wave, Classic, and Azure. Now, the goal is to basically bring work with our customers in Alberta, Canada, North America, and globally to solve their quantum machine learning, optimization, simulation problems using quantum computing. This is a special relationship, and the goal is to create a client-focused quantum computing ecosystem. Just hold on, sorry. And here we have joined hands together with University of Calgary for the Quantum City initiative. They are the training partners, talent development, R&D partners for this partnership, where Mphasis brings in industry relevant innovations and use cases. Sorry, job creation, technology partnerships, and all. This collaboration, the goal is to do quantum awareness and training programs for industry, build a quantum readiness engagement model for adoption of quantum computing, access to industry, scientific and technology experts, all this. Now, since we are addressing client needs, there has to be an engagement model is placed. Our goal is to get our customers quantum ready. The technology is taking pace, and a late adoption has consequences. So given that idea, we want our customers to start exploring quantum technology, and for the same, we have built an engagement model. So this is the engagement model for quantum computing adoption. Here, if you look at it, we have divided this into 4 parts, given the novelty of this technology and the awareness in the market. So we start with quantum awareness sessions. The idea is to help you create an in-house team or COE to focus on your quantum computing goals. These take the form of a workshop, which can be customized based on audience. So it takes business, technical, and strategy point of view. Now, this generally runs throughout the engagement. We don't want to run it at the very start. It depends on when the right audience is available or when they are ready. Now, other than that, what we start with is an assessment workshop. The idea is basically you don't know where to apply quantum computing. We come and help you out. If you don't, if you already have a team in place, you don't need to do these workshops. But the idea is during this design thinking driven phase, our experts work closely with you to identify, rank, and prioritize use cases. So you identify the use cases, you look at parameters like whether this use case benefits from quantum computing or not. If it benefits, how much benefit you'll get, whether it will make decent noise in your organization to take quantum computing forward, and many more things. Do you have the right data in place to solve this use case? And finally, we take one use case. Now, the next step is a consulting workshop. This is in this case, we basically address 2 major objectives. If you don't have a quantum computing service provider on your side, we help you identify the right one. So the idea is, for example, if you want to solve optimization use case at scale today, I would say that go with D-Wave's quantum annealer. If you say no, we want to do machine learning, I will say let's explore some gate-based systems from IBM, Atom Computing, and others. So that we help you with. Then we also do some deep dive and fine tuning of shortlisted use cases. So the use case that we have shortlisted in the last phase, we looked at those and we basically try to uh, deep dive into it. What data would you require to solve this use case? What kind of KPIs you have today? How will the system be integrated? How will it work over cloud? All those things we address in these workshops. And finally, when we are done with all this, we jump into a longer session, a longer phase, which is a quantum solution development. This we work with you to design and implement the solution. The goal is not to build a solution and hand it over to you and run away. The goal is that we build it and we have continuous sessions with your team to help you understand how it is being built, so that when you pick up the next use case, your team is also ready, even if not to execute, but to understand what we are doing and assess the same. Sorry. So now this is the engagement model, but how do we execute this engagement model? So this, we have taken a pod-driven model for this pod-driven delivery model. The goal is that your use case, and it can be oriented towards IP development, client delivery, capability building, any of those. Each pod is a self-sufficient entity, which contains a quantum project lead, a technical lead, a domain expert, a quantum developers, project managers, who look at your use case and apply those 4 phases to it, the ones we saw earlier. These people are they're multidisciplinary in nature. They understand business, they understand technology, and they work together to solve this problem. Now we have a strategy pod also in place, which basically is multidisciplinary, Mphasis and partners. And they look at the direction we should take to build solutions, address the different strands of quantum computing, which partnerships to take, so on and so forth. So this helps you in getting a guidance on where the technology is going. And we have some very strong partners like University of Calgary, where we have who are experts in this field for more than 30 years. Now they know in and out of this technology. We bring the industry angle as well. Now these are the 3 use cases we have done till date, and we are addressing a few more right now. The first one is the last phase of the engagement model. We were given the use case. All we had to do is to apply quantum computing to the use case. We did not do awareness sessions. We did not do assessment or consulting workshops. In this, we applied a last mile route optimization solution that I talked about earlier to a last mile container container delivery with reverse pickup. So this was a 5-month project, and this was done for one of the largest freight service providers in North America. That is one. Now, next one is a quantum readiness program that we ran for one of the largest American healthcare companies. This was recently concluded. This again we did for 5 to 6 months. Here we did the end-to-end engagement model that I talked about: awareness session, assessment model, consulting model, as well as the quantum solution development. They started with a team of 0 people who was part of their quantum team. Right now, they're working with 5 people in their team, addressing different areas. Finally, the last one is an interesting one. It is ongoing, but the goal was, given bodily fluid samples, can you identify the chemical profile that exists within your blood, your serum, your urine, and come up with the pathogens that exist in your body? So that can be addressed using a machine learning solution, and we applied quantum machine learning for it. So in this case also, the problem was given to us. All we had to do was quantum solution development. Now, this is my last slide, and after that I can take questions. This is the analyst response we have received from our work in this area. So from HFS Highlight, Global Data, 8 Novarica, Gartner, all of them have looked at our work and given these comments. So this is where I'll stop. Over to you, Vivek or Taylor, and I can address the questions.
Awesome. Thank you, Rohit. Great work. We do have a couple of questions in the chat. And then once we get to those, if anyone would like to unmute themselves and ask any questions, please feel free. The first question is from Naveen, and they ask, does quantum computing require specific hardware or chip?
Yes. So quantum computing itself means a quantum computer, a different type of computer. It requires a chip based on principles of quantum physics and quantum mechanics. And these chips are available from different hardware vendors over cloud. So IBM has it, Google has it, Pascal has it, Atom Computing has it, and they have provided it over quantum compute as a service providers over cloud. IBM Quantum Experience, AWS Bracket, Azure Quantum, all of them provides hardware and software tools for you to solve the problem.
Awesome, thank you. Raphael asks, it's a bit of a three-parter, so I'll start, and if you want to address it in three different parts, we can. Raphael says, can you explain energy savings when using quantum computers to run these solutions? Do quantum solutions run on real time, or do they apply to batches and queues?
Okay, so I'll address these one by one. The first one about energy savings. So I do not have an exact answer with this, but the idea is this, that right now, many computers that are available today, the system has to be cooled down to say below zero kind of a thing, right? So given that a lot of energy is expended, but room temperature quantum computing using photonics is also being addressed, and they will consume very low energy. The reason being is these are reversible computations, a special thing that you have to look at, that during computation, they do not lose energy. So the overall cost to run these is going to be low. That is my understanding. Now, are these quantum solutions for real time? So let me take it in form of an example. If you talk about machine learning, let's say, when you are training the system, it's a similar task as what you do in a classical machine learning, only the backend compute has changed. But when you look at running the inference, they will be real time. You can basically you can provide your batch data or streaming data, and they can predict what you want to predict. So it applies to batches, it applies to queue. It depends on the type of problem you are trying to address rather than the technology. You can look at the classical technology, how it addresses these problems. The exact same thing will be done by a quantum computer. There is no difference. Only thing is backend machine has changed.
Awesome. Thank you, Rohit. Just a couple of more for you before we head out of here. The first one is, will quantum computers, once mature, replace classical computers?
Okay. So no, they will not. So as I said earlier also that today also there are different computers that exist, and each has their own specific task. Quantum computer will also have some task which it will excel at. For example, it is a very important technology for fields of chemistry and material science. To find new materials or drugs or do drug discovery is not easy on a classical computer. Quantum computers can give a big advantage there. For example, they're not going to be used for web search. Classical computers do that well enough. So no, they are not going to replace it, but they'll work with classical computers, similar to how QPUs, your GPUs, physics processing unit, and all that work together to say build a gaming system today.
Amazing. And the last question we have here, I think this is really important too, is what should be the timeline for adoption of quantum computing?
So nobody can say for certain. Numbers, the answers are different. Somebody says that proper fault tolerant large scale quantum computing will available only in a decade. But that does not mean the quantum computers that are coming up slowly in or will come up in a course of 1 or 2 years will not change the way your operations can be realized. So your operations still, you are not looking at exponential advantage, but some advantage which gives you cost savings. So from that perspective, adoption should be faster. Another reason is it is not an easy technology to master. It requires an organization-wide adoption. Given these two things, it takes time. It is not easy to adopt it immediately. It's not like, for example, when we switched from CPU to GPU for certain tasks, still it was not that difficult. The underlying technology is same. The principles of programming are same. Many of the things are same. and we were able to address it. Here, the whole programming paradigm itself is different. You're looking to use superposition, interference, and entanglement, very physics-based concept to write programs. But if you can understand them well enough, and you can write certain solutions, the advantages are humongous. And people do understand it. Your whole organization do not have to switch to quantum. You need a small team to begin with, which understands quantum, and then grow that team slowly. Hence, we are working this getting quantum ready model, where we start with a small team and then subsequently grow them up so that you can get the advantage in the longer run. It will be applied in certain scenarios. Again, as I said, it won't be applied in each scenario, so you need a particular team size to get the benefits.
Awesome. Somebody has a question here with their hand raised. Please feel free to unmute yourself.
Thank you for the presentation. This was really great. I wanted to ask about the commercialization of quantum computing products in the SaaS space. Just like how we're seeing the proliferation of AI products and machine learning products in SaaS, how many years do you think before we start to see off-the-shelf products that allow us to be able to solve very specific forms of quantum problems?
So you can, so SaaS, so if you talk about SaaS products can come out anytime, but the idea is the only issue with quantum today is solving problem at scale. So even if I give you a SaaS-based solution today, and we already have a SaaS-based solution deployed on Azure for anomaly detection, you can use it. The problem is when it comes to scale, it may not satisfy the requirement you have. The scalability is a bigger problem than the SaaSification of it. So people are trying to solve the same, but still, as I said, few days back, only 10 days back, this 1000 qubit computer has been launched. As I said, when it became 50 qubit, it already surpassed the capability of a classical computer, had it been fault tolerant. 1100 is a big number. If they achieve fault tolerance tomorrow and connectivity, you see that the scale has changed completely and you can address some large problems. SaaSification will not take time because everything that you do today on a classical computer, the way the APIs work, the way the solutions are deployed, nothing changes. Right now, also, all the solutions that you saw that today, we made API calls to a quantum computer to get the result. The programming language used was Python. Nothing changes from that perspective, only backend machines are changing. So SaaS solutions can come up anytime, but will they be useful or not is the bigger question at this point in time.
Awesome. Thank you, Rohit. Last call for any questions before we wrap up for the day. Okay, well, thank you all so much for attending today. Rohit and Vivek will be able to send you all the slides. They both have your contact information, and this recording will be uploaded in a couple of days on the Toronto Board of Trade's website, YouTube website. So stay tuned for that. And again, thank you all for attending today's session and enjoy the rest of your